Andree Jacobson from New Mexico Consortium, and we're gonna do a couple different talks here. So we're gonna start out high performance computing. We're gonna try to tell you everything about high performance computing in 90 minutes.
Yeah.
You're gonna be masters of it, right? Now this is a field that takes a long time to learn. We're gonna try to give you a little bit of a feel for it. So first of all, high-performance computing is about the science. It's about the application, not about the computer. You hear that, computer scientists? Where's our system guides? You remember that? It's about the answer, not the computer. I know you like us to buy you big toys. So we're going to start off with the Lost Conscious Fire. How many of you remember the Lost Conscious Fire? So Lost Conscious Fire was up in Los Alamos. We had 2 or 3 big fires up there. Actually, if you go back in history, a lot more. But these were much bigger than normal. And so we have a group at the lab that studies that and simulates it. And so what can you learn from a simulation of a fire? So this is by Rachel Robey. She works at Lannel. She's one of my favorite students because she's my daughter. And she's a senior at the University of Colorado. So let's go ahead and this is a video, so popcorn is coming out. Uh-oh. Do we have a way to hook up speakers? She's prepared.
You're not wireless, Taylor? Next second. There we go.
Does that work? Okay. Okay, let's try it. That's not sounding very loud.
It's even lower.
We'll do one of those bad lip reading renditions of this.
So what you need to prepare about is
Oh, and reset.
and look at different suppression methods and ways to protect. So the major physics module that we have that we add on to high grad is called Fire Tech. And we use it to study wildland fires, which has a ton of different applications that are incredibly relevant, especially in the Southwest. It's an award-winning model, and it allows us to predict fire behavior, better understand fire behavior, and look at different suppression methods and ways to protect, say, lab resources or homes, and so on. Which brings us to a somewhat interesting case study coming from Los Conchas fire in the summer of 2011. So it began on June 26th, and spread incredibly quickly that first night. So to give you an idea, in 2000 we had the Cerro Grande fire, which was the largest in Mexican history, and in total, over its entire lifetime, it burned somewhere around 48,000 acres. This fire, in the first day, grew to 42,000 acres. First day. It lasted until I think it was finally declared to be extinguished at the beginning of August. So this defied pretty much all traditional fire knowledge. Normally at night, as the mountain layer stabilizes and it cools down, fires would be somewhat more retarded and they'll die down a little bit. Fires typically spread uphill. And in sparse fuels, things spread so much as quickly. So why? Why did it behave this way? Why was it driven down canyons? Down, and it exploded overnight. To get an idea, this is a map. So this blue here is its spread in the first day, and the lighter blue the day after. And these are stats from it. To get an idea, we can look at some of the weather information from that day. And you might notice that right around overnight, going into that Monday, there was a significant and quite change in wind direction, as well as wind speed. So my group was studying sort of this behavior and came up with a theory about interaction between fire behavior and the interesting topography that we have around Los Alamos. So like I said, fires typically lay down and burn slower, but the topography and sort of these waves influence that. So specifically came up with in this case is the pyrocumulus column collapse. So as the fire was first burning, it was sending aloft lots of soot, ashes, and so on that it was building up this big pyrocumulus cloud, or column, sorry. And then when at night there was a sudden shift in wind speed and direction, there was no longer the hot air to sort of sustain this cloud. So it came down, creating sort of gravity wave, or density wave, that drove fire down the canyons, which you don't typically see, and created sort of these winds that drove. So this was a simple model of just building and collapsing a column like that, which you can then see, you might somewhat recognize this topography a little bit, the mesas around Los Alamos. So this is a theory that they were testing out and has worked out fairly well. So this is colored by the vertical velocity. So you can see there's a lot of downdraft, which is driving down those mesas. And here we have that same density current. You kind of see it coming in. This is the same view, just different parameters being checked. We have the density current coming in on the far left over there. And we're going to watch the effect on the fire line down here in the bottom view. These are all velocity vectors with the heat in the red at the bottom there, so into the fire line. So as you see it hit, you can see it just sort of explode. And you start to see these downward vectors as the fire is driven down, or sorry, the winds are driven down, all that hot air can then ignite the fuel in front of it. So the rate of spread skyrockets, and you start to see very atypical fire behavior. And as this evolves, you start to see it creating a bit of a vortex where it re-entrains some of this dense material and continues to drive down the fire down back into the head.
Okay, so that's just a small little example of some of the science we do with that code. We do a wide variety of science, but that's what this is all about, is getting that kind of simulation to help us understand the behavior of what's going on. We're putting in a proposal for that group to do a simulation of the fires in the southeast and try to understand what happened there. The holy grail would be to be able to do it in real time and have the fire crews actually respond, know how to manage the fires. So the next video, let's see, I'm going to introduce it here. Is on performance. So once you get the science, you want to be able to get performance. You want to be able to do bigger problems. You want to do them faster. That's one of the keys of high performance computing. But before we do this, anybody ever hear about premature optimization? Okay, so we're going to talk a little bit about algorithms before we do this, and I'm going to give you a chance to all get up and do a little algorithm development here. So one of the algorithms we've been developing is how do we do things like hashing or finding where we are in space on the GPUs. So I want you to pretend this is a GPU. Each of you is a work. So a work group and a GPU. And the GPUs are very fast, and they got lots of processors, very lightweight processors, but this warp or work group cannot communicate with the one behind it, or the one behind it, behind them. You can communicate within your own group. So we're going to do a little algorithm here. I want you to do a sort. I want you to do this. First of all, let's do a shuffle sort. So let's say you guys here are going to compare badges. If your last name is earlier than the one to your left, you're going to move to the left. If it's lower, you're going to move to the right. Okay, are you timing? This is going to go in the paper. Okay, we're going to have a race here between the rows here. Okay, we'll make it a little easier. You can just trade the name badges. Okay, this is like trading the pointers. We don't move the whole data element, we just move the pointer. Okay, 1, 2,
You only do it once or?
no, keep doing it till you're completely sorted. Let's go. Timer's running. Have you ever done algorithm development at a conference before?
Since last week.
Okay, if it's lower this way, C's over here, A's over there. Last name, first letter.
My first name or last name?
Yes.
My first last name. My last name?
Last name.
Well, okay. Oh, fine.
Okay.
Yeah, you can communicate within your work group, your work.
Okay, on this side. Okay, so, yeah, we're going that way. So, higher alphabet, so A, B, C.
So we have
C's over here, A's over there.
Okay, so C's are going that way, A's are going that way.
Oh, then here to.
Okay, first row's done. Anybody else? Okay, you were done half an hour ago. You were done before you came in the room. All right.
Oh, the last name.
Okay, so, are we sorted?
No.
We're not sorted here. How do you communicate?
Okay.
You can't, in the kernel, get these 3 rows to communicate on the GPU. So how do you handle that?
I'm gonna yell.
Huh?
I'm just gonna start ordering.
So you actually have to exit the kernel and do something else to do the ordering. So this becomes very hard. So you've got good communication in a small group, but not global communication. The lack of global communication is why the processors are fast. They don't have to cooperate with each other. Okay, you don't even know when they're scheduled. You could be scheduled in any order. Okay, so this is kind of hard to do this algorithm here, but that's been a traditional algorithm. Let's try a different algorithm. Let me put the letter A here, B here, C here, all the way to Z. Then I'm going to tell you to take the name in your hand. I know it's not yours, mostly. And just come up here and line up in the box with your name. We can imagine this, okay? Unless you guys want to get up and do it. No? Catherine says no. No, it's not Catherine anymore. It's Chris. Okay, Chris, you okay with that? Maybe? Okay, so think about that. How much communication do you have to do that operation? How many, order complexity, the shuffle sort versus this one, what's the difference in complexity? So this is an order 1 operation, you only have to do 1 step, you move once. Power is related to moves, so we have a much more power efficient algorithm. The shuffle sort is more of a log n-ish type algorithm, so it actually takes more time. And I say this hash-based sort where you create bins and everybody moves up into it. You might have to do a subsort here if you got a few people in a bin. But I call this the perfect algorithm for computational scientists. You guys don't have to talk to each other. No communication. Yeah, you can just look at your shoes and walk up to them. But it's actually very good for GPUs. So a lot of our algorithm development has to change because of these new architectures. And it's up to you to come up with these changes because the traditional algorithms don't always work well on these. Okay, so now we've got the right algorithm, we can optimize. Do you have questions about that algorithm? Have you ever done that algorithm before? It's not in the textbooks. Textbooks are always right, aren't they? Okay. So here's another. Okay, this is Peter Ahrens. He's one of my students for a few years and now a valued colleague at MIT. He is a super programmer, one of the best I know. He's going to give you a 30-minute view on how to optimize, vectorize, OpenMP, and MPI. We would have loved to have you do this in a hands-on session, but usually they sort of fall apart, so he's going to actually list a site. You can go and get his code and experiment with it. Okay, this is the Game of Life code. So it's a very simple code. I do not say that every technique he uses here is appropriate for every code. He is a super optimizer. Okay, so let's listen to Peter.
Matrix multiplies time to start the tutorial. I'm Peter Ahrens, and I'm here to show you a little bit about performance tuning. A lot of performance tuning tutorials tend to show you several techniques like cache blocking or loop enrolling, and they don't really show you how to fit them together. My hope with this tutorial is to kind of remedy that by showing you how I would optimize a particular program. And so I'll take you through all of the performance tuning techniques that I would do to optimize a very small program. In this case, it's the Game of Life.
Throughout this video, we're going to be looking at snippets of code, which is incredibly boring if you don't have your own code to look at. So I would encourage anybody watching this tutorial to go ahead and check out a copy of the repository, and break things and make mistakes and get messy.
In this tutorial, we're going to be studying Conway's Game of Life. This was a cellular automata developed by John Horton Conway. A cellular automata is essentially just a rectangular grid of cells that each have an on or off state. The cells all have an initial state and will turn on and off according to certain rules, so they evolve over time. In the Game of Life, the rules that govern our cells are that when a cell has less than 2 neighbors, it'll die. So this cell here should die. If a cell has 2 to 3 live neighbors, then it'll continue to live. So for example, this cell here should live because it has 3 live neighbors, as should this cell because it has 2 live neighbors. If a cell has if a cell has exactly 3 live neighbors and it's dead, it will become alive. So this cell here should become alive. And then, of course, as you can imagine, all sorts of mischief goes on in the world of life here. I mean, it's a beautiful, complex machine that kind of evolves over time. Okay. So that cell was alive and then promptly died because it had no other neighbors. That cell became alive. Here we have this is called a glider, and this one blinks. But life can actually get pretty complicated. This pattern is called the acorn. It's the first pattern that John Conway couldn't fit on a billboard. He used to do simulations on a billboard. So, anyways, it's kind of exciting and very complex. Anyways, this is the game of life, and this is what we're going to be simulating. This is what we're going to optimize. All right, let's get into the thick of it. So, if you're following along with the code, it's available on GitHub. We're going to start by looking at the reference implementation. And I'm going to kind of try and give you a little bit of an idea of what's going on here. So here we go. This is our reference function. And so it takes in a height and width of the grid, an initial state, and it's stored as a matrix of unsigned numbers, and a number of iterations to simulate for. So the goal of this function is to tell me the state of the life grid after this number of iterations. One important way in which our life implementation that we're simulating will differ from what you just saw is that our simulation will wrap around the sides like Pac-Man does, so that it's a boundless environment. So here we make we call it the universe. This is the current game of life grid. We store alive as 1 and dead as 0. We go ahead and allocate that, and then we have a new array to store the results of the next iteration in. So first we load the initial configuration into the universe. Now our universe is set up. And so for each iteration, for each row, for each column, and then we have a cell, right? So this is basically for each iteration, and then for each cell, we're going to loop over all of the neighbors of the cell and count how many neighbors are alive. So here we are, we iterate over y and iterate over x, and this particular set of loops here is a little bit redundant because alive is represented as 1 and dead is represented as 0. We could just add the contents of the universe at each neighbor together in order to get the number of alive neighbors. But instead we're going to go ahead and just double check. We're going to say if universe, and then we find the position of the neighbor and increment a counter. N is how many neighbors we have that are alive. And then we go ahead and avoid double counting ourselves. If you'll notice, this loop actually counts us as well. It actually counts the current cell as well as its neighbors. And then here, there's kind of a beautiful, tight bit of logic based on the number of neighbors to tell you whether or not the new cell at this location will be alive. And this is what performs that sort of logic of if n is 3 or if n is 2 or whatever. And then at the end of the iteration, we copy all of the contents of the new cells into the universe, and our universe has advanced 1 iteration. So, as you can imagine, this isn't exactly the smartest way to do it. There's a lot of things that can be improved here, and indeed we're going to go through them. But why don't we just focus on the simple things that we can do to make this run faster. So we've stored that in simple.c, a community name. So here we have this is like our reference function, except we've made a few modifications. We still have a universe and a new matrix, except this time we can directly add the universe values to n, and we don't have to use that little if statement to check and then increment n. We can just go ahead and add the contents of the universe, and that'll give us the number of alive neighbors. And of course we have to subtract ourselves here. And then this next step does the same logic. Now, instead of copying the new matrix into the universe matrix every time, what we do is we can swap the pointers of universe and new. So now universe points to new, and new points to universe, because if you'll notice, we don't actually, in this entire inner loop here, we never read the contents of new, we only write to it. So that's what lets us do this pointer optimization, where we can swap the pointers. Let's compare our simple optimizations to our reference version. We have a little bit of code to do that. Bench.c, our benchmark file. And as you'll see here, it has the same timing code that our matrix multiply example had in order to get a decent sample size and to load the thing into cache as much as we could, etc. Another important feature that this code has, all benchmark files should probably have, is that it checks that the results of the reference version match the results of the optimized version. If you don't have a check like this, you could run the risk of spending a lot of time on your optimizations and then realizing that they don't work at all. So if you can, definitely check that your results are right as you optimize. So here, let's go ahead and actually run our code. Here we're going to compare the results of our simple optimization on an 8,000 by 8,000 grid for 256 iterations. And the results take a long time to come up, so I'm going to skip to when they actually do. Okay, so we have our results. It seems that the simple optimization gave us a pretty good speed up of about 1.3. Now we're going to look at another optimization that we can do, because 1.3 is good, but we can definitely do much better. So padding is an important trick that a lot of people do when you're trying to optimize code that operates over a matrix. If there's special routines or special logic that you need to follow when you reach the edges, in our case we wrap around the edges, it often helps to pad the edges of the matrix with a copy of the wrapped around version. Okay, I'm going to try and explain this to you guys by drawing a bunch of rectangles on a piece of paper. So, just pretend this is our universe matrix, and this is our new matrix. Now, if we want to compute, say, this cell in the new matrix, then we'll have to compute these cells, or we'll have to, that depends on the value of these cells in the universe matrix. We want to compute this cell in the new matrix. That depends on these cells in the universe matrix. Now, going all over the place to find these cells isn't very good for our caching performance, but at least we only have to do that for the cells on the edges. However, the logic that we use to calculate where these cells are is rather complicated. It involves a little bit of modular arithmetic, and we're doing that for all of the cells inside of this new matrix, when we don't have to, because we can just look up, down, left, and right without worry of hitting the sides of the matrix. So wouldn't it be great if there was a way to fix this? Well, imagine we made our universe matrix a little bit larger. So what we're going to do is we're just going to add one little layer to our universe matrix. And this layer represents the wrapped around version of what you would find if you went over the edge on this universe matrix. So for instance, right here, when we're at this edge, and we look at this cell, what we want to put in this cell is what we would find at this bottom edge of the matrix. So really all we're doing is we're just pre-computing all of the complicated cases and storing them where we would expect to find them if the matrix were truly boundless. This is a general technique that you can use for not just wrapped around grids, but say you assume that you have zeros on the side. You can go ahead and just put some zeros if you're doing a scientific computation, something like that. Anyways, padding is a pretty general idea. Now, if we're going to go ahead and swap our pointers, then we're going to have to pad the new matrix too. But because we don't want to do our complicated arithmetic, what we're going to do is our loop is only going to compute this innermost layer. It's only going to compute the inner rectangle, and the outer rectangle we're just going to use. We're just going to leave that alone. And then at the end of the iteration, we're going to go ahead and copy all of the values from the top row to the bottom
part of the layer and from the bottom row to the top part of the layer. And then that way when we swap the pointers, everything's okay for the next iteration. Now, what would happen if we didn't do the copy at the end of the iteration? And what I mean by that is, what would happen if instead of doing the copy, we just had a valid, our universe was valid, but this outermost row wasn't?